Welcome to the Preschool Transitional Kindergarten Learning Foundations, or the PTKLF, presentation of the math domain. This pre-recorded presentation is part of the series of presentations developed by the California Department of Education in partnership with WestEd that follows the release of the PTKLF to provide a snapshot of each domain covered in the publication. This presentation is focused on the math domain, and we are joined by the writers of this domain, Sophie Savelkuls and Osnat Zur. For an overview of the introduction of the PTKLF publication, including its structure, organizations, and major revisions, please visit our prior pre-recorded presentation titled Preschool Transitional Kindergarten Learning Foundations Introduction on CDE's YouTube page. The agenda for today is to provide acknowledgements for the contributions of this specific domain, provide an overview of the organization of this domain, and provide examples of foundations in each strand. So one for counting and cardinality, operations and algebraic thinking, measurement and data, and geometry and spatial thinking. Then we'll provide an overview of the diversity of children's math development, followed by a brief section on how teachers can support math learning. We will end with a closing and a look at future pre-recorded webinars. We also wanted to take a moment to list some acknowledgements for individuals who contributed significant time to the development of this domain. In addition to the California Department of Education and WestEd team, we had our WestEd lead writers, I mentioned previously, Sophie Savelkuls and Osnat Zur. We also consulted with subject matter experts, Douglas Clements from the University of Denver, Megan Franke from UCLA, Linda Platas from San Francisco State University, and Deborah Stipek, emeritus from Stanford University. We also had specific reviewers who brought the lens of inclusion, cultural diversity, or multilingual learners. Felicia Mensah from Teachers College, Columbia University, Margaret Gillis from SRI, Mary McLean from the University of Florida, and Juliana Meltzi from NYU. We would also like to thank our many, many educators and interest holders who participated in focus groups and provided feedback. I will now pass it on to the WestEd lead writers to talk through the details of this domain.
Thank you, Lily. And let's first review the overall structure and organization of this domain. Next slide. The math domain describes math development in children ages 3, 5.5 in high-quality early education programs. We'll start with the organization of this domain. The math domain includes 8 mathematical practices and foundations organized in 4 strands. The first strand, counting and cardinality, includes substrands on counting principles, recognizing quantities, numerical recognition, and number relationships. The second strand, operations and algebraic thinking, includes substrands on number operations and classifying and patterning. The third strand, measurement and data, includes substrands on comparing and ordering, and the substrands on data. And the last strand, strand 4, focuses on geometry and spatial thinking, and it includes substrands on shapes and on spatial thinking. So before we go into the foundations, here is an example of how the foundations are structured and organized. Each foundation is numbered with the first number representing the strand and the second representing the order of the foundations within the strand. So for example, the foundation on the screen is named reciting numbers, and it is numbered 1.1. It indicates that it is part of the first strand, counting and cardinality, and that it is the first foundation within that strand. Next, two foundation statements appear underneath this label. In the left-hand column, we have the early foundation, which describes the skills and knowledge children demonstrate between the age of 3 and 4.5. The foundation statement in this age, for example, says, recite numbers in order from 1 to 10 or higher, with no more than a few errors. In the right-hand column is the later foundation, which describes the skills and knowledge children demonstrate between the ages of 4 and 5.5. The statement for the later foundation says recite numbers in order from 1 to 30 with no more than a few errors and count forward from a number other than 1. So these are the two foundation statements. And then finally, below the foundation statements are a series of examples. In here, we only show one example to demonstrate, and you will see in the full document that the first one or two examples for each foundation are aligned to demonstrate the developmental progression more clearly from early to later. Next, before we dive into providing examples of foundations, let's take a look on key differences from the preschool learning foundations in 2008 and the current version. We really want to make a general note about some high-level changes you will see in this version. And first is that in our revisions, we made sure to have very close alignment with the organization of the Kindergarten Common Core State Standards. The strength structure and naming in the PTKLF is similar to the Kindergarten Common Core Standards. So for example, you will find that the strand operations and algebraic thinking is named to match the same strand in the California Common Core State Standards. Second, we have included the same mathematical practices that appear in the Common Core State Standards into the document. We will review these mathematical practices more closely in a moment, but the decision to incorporate these was to have a closer alignment with the Common Core State Standards and to indicate the importance of these practices from a very young age. In terms of the math content addressed in the standards, we expanded on a few different areas. First, for the math area of geometry, under geometry and spatial thinking, we added a foundation on how children learn about three-dimensional shapes in addition to two-dimensional shapes. So that's a new one. We also added the foundation focusing on children's spatial thinking. Research suggests that spatial thinking skills are an important part of children's learning in math, and therefore we have highlighted this by dedicating additional foundations specifically on spatial thinking in this version. And then finally, we included two foundations on data. Again, children between the ages of 3 and 5 can learn about how to represent data, how to interpret data, and these skills are described in two new foundations. I will now invite my colleague, Sophie Salvakus, to provide a review of the mathematical practices and examples of foundations from each of the strands.
Thank you. So an important part of this domain is an emphasis on the mathematical practices. These mathematical practices describe the types of behaviors and dispositions that allow children to develop knowledge and skills in mathematics. The mathematical practices are not the same as the foundations because they do not have two age groups, but these mathematical practices are identical to the Common Core state standards for mathematical practice, as was not mentioned, with added descriptions that show how these practices apply to young children. So let's take a closer look. The first mathematical practice is making sense of problems and persevering in solving them. This includes applying mathematical thinking to solve problems in everyday activities and interactions, and persisting and trying a variety of ways to solve a problem. For example, bringing over 2 plates to set the table for 4 people, and then noticing that you didn't bring enough plates, so you add 1 more, and then realizing that 3 is still not enough, so you need 1 more to make 4 plates. The second mathematical practice is reasoning abstractly and quantitatively. At first, children reason about abstract mathematical ideas like quantity using very concrete objects, but over time they can relate to mathematical problems in a more abstract way. For example, communicating, I have 2 people in my car and you have 1, so we have 3 people altogether. Over time, children are able to relate to mathematical problems in more abstract ways, and so they might say something that like 2 + 1 = 3 without the support of objects. The third mathematical practice is to construct viable arguments and critique the reasoning of others. This includes constructing arguments about solutions, like how many more blocks are needed to complete the wall, and explaining reasoning. For example, I think we should use the smaller blocks because they fit better in this space, and then critically thinking about the solutions of others. The next mathematical practice is modeling with mathematics, which includes using models like drawings, constructions, and modeling with their own bodies to illustrate thinking and solving mathematical problems. So, for example, this might include first drawing what your structure might look like before actually constructing that structure with blocks. The fifth mathematical practice is using a variety of tools to solve mathematical problems. So this might include tools like a scale to find out which toy is heavier. The next mathematical concept is applying mathematical skills with increased precision. For example, knowing you need 12 bowling pins to play, so you count with precision to figure out how many you already have and how many you might need to make it 12. Then there is the mathematical practice of looking for and making use of structure. This includes recognizing structures and rules in mathematics, like knowing, for example, that all squares have 4 sides. Then lastly, there's looking for and expressing regularity in repeated reasoning. This includes noticing patterns and regularity in mathematics, like knowing that a whole number plus 1 is the next number in the number list. So now we have reviewed the mathematical practices. Let's take a look at some samples within each strand. So I encourage you to reflect on any of the mathematical practices we just mentioned as we walk through some of these examples or sample foundations. The first strand is counting and cardinality, which focuses on children's ability to recite numbers, use one-to-one correspondence, and understand the concept of cardinality. It also describes children's ability to identify the quantity of small groups of objects without counting, like subitizing, compare quantities, and also recognize numerals. So let's take a look at one sample foundation from this strand. So this sample comes from the Counting Principles substrand of the strand Counting and Cardinality. This foundation focuses on cardinality, or the skill of understanding how many. You will see that the early foundation is being able to answer the question how many by counting, and sometimes a child is able to indicate that the last number counted represents the total number of objects. So for example, when asked how many, A child in this early foundation may count their items 1, 2, 3, 4, 5, but does not explain or repeat that they therefore have 5. Even if you were to ask again, so how many is that? The child may count again, but not answer that there are 5. At this stage, children have not quite understood that the last number in their count list is how many. However, in the later foundation, when you ask how many, the child counts 1, 2, 3, 4, 5, and then can answer, I have 5. The second strand is operations and algebraic thinking. This describes children's ability to solve simple arithmetic problems and reason about ideas such as adding to, putting together, taking apart or taking away, and sharing. Additionally, this strand describes children's abilities related to sorting and classifying objects by their salient attributes, as well as recognizing, duplicating, and extending and creating patterns. So let's take a look at a sample foundation from the number operations substrand, which is within the operations and algebraic thinking strand. This sample foundation focuses on principles of addition and subtraction. The early foundation is focused on demonstrating and understanding that adding or taking away one or more objects from a group will increase or decrease the number of objects in a group. So what does that look like? For example, when a child hands a teacher one more block, they are able to express that the teacher now has more blocks than before. Then in the later foundation, children can begin to articulate how the quantity changes with adding one or taking away one. So when they give the teacher one more block, they might communicate, there were 4 before, but now there are 5. You can tell how the progression is a child going from understanding that adding increases the number of objects and that taking away decreases the number of objects, to in the later foundation, understanding that when one object is added or taken away, the quantity changes by exactly 1. The third strand is measurement and data. This describes young children's understanding of how objects can be compared, ordered, and measured by a variety of attributes, such as length, weight, or capacity. The foundations on data describe children's ability to collect, represent, and interpret data. So let's look at a sample foundation from this strand. This is an example from the comparing and ordering objects substrand, which is part of the measurement and data strand. This foundation is focused on comparing measurable attributes of objects. So you will see that the early foundation is focused on demonstrating awareness that objects can be compared by different measurable attributes. So for example, a child might hold one toy and then another, and point to the heavier toy and communicate more heavy. Then in the later foundation, children can begin to more precisely compare and use language to describe or explain the comparison. For example, with the help of a teacher, a child might use a balance scale to find out which of 2 toys is heavier. When the teacher asks which one is heavier, the child might point to the side of the scale that went down. And then if the teacher asks, how do you know this one is heavier? The child might respond, because it went all the way down. You can tell how the progression goes from a more broad, general understanding that objects can be paired by a measurable attribute to comparing objects by length, weight, or capacity. For example, putting 2 objects against each other and communicating which one is longer, or putting 2 objects on a balance scale to find out which one is heavier. Lastly, we have the strand geometry and spatial thinking. This describes children's ability to identify, describe, and compare both 2- and 3-dimensional shapes by noticing a shape's attributes, so that might be things like points or sides. This strand also describes children's ability to identify positions and directions of objects in space, and to use spatial vocabulary, and to develop the ability to mentally rotate, flip, or slide objects to solve problems. Think about rotating pieces of a puzzle. This sample comes from the shapes substrand within the geometry and spatial thinking strand. This focuses on identifying two-dimensional shapes. So the early foundation includes identifying familiar two-dimensional shapes, such as a circle, square, a triangle with equal sides, and a rectangle. It acknowledges that children may not identify non-typical versions of a shape, like a square that is turned so that the point is down, or a triangle that's not an equilateral triangle. So in this age group, for example, a child may only pick out equilateral triangles from a pile, but not atypical triangles, like a triangle that has different length sides, like isosceles or right-angled triangles. In the later foundation, children not only identify the shapes, but can describe important or defining properties of a shape. For example, in the later foundation, children may describe that a triangle is a triangle because it has 3 sides. You can tell how the progression goes from identifying some familiar two-dimensional shapes to being able to understand what defines a shape, such as the number of sides or points. I will now pass it back to my colleague Oznat Zur, who will talk about diversity of math development.
Thank you, Sophie. So in this next section, we want to highlight the importance of diversity of math development among children, so that as you use the preschool TK Learning Foundations, you keep in mind this diversity. So let's take a first look on culture and culturally responsive math learning. Children enter early education programs with a range of mathematical experiences, and this is based on their home and community environments and family values related to mathematics. Traditions and routines in the home and community really provide children with natural opportunities to develop mathematical thinking. For example, rug weaving is an important practice in Native nations and tribal communities. Rug weaving involves creating intricate designs using various colors of yarn on a loom, and this can expose children to mathematical concepts like patterns, shapes, and measurement. So teachers should capitalize on the mathematical opportunities that are present in the child's home and community life and provide learning experiences that allow children to engage in mathematical thinking through cultural activities, traditions, and routines that are meaningful to the child. One way to consider this in your own program is the materials you choose to use for math. Math doesn't have to involve just blocks and counters. It can be natural materials you find outdoors, or the use of art, music, and integration with literacy activities like stories that are meaningful to children. Next, we'll focus on linguistic diversity. Children's linguistic background can impact the way they learn and express mathematical ideas. Languages vary in how they represent mathematical concepts, including their number naming system. So for example, languages such as Chinese or Japanese have a number system in which number words map directly into a base 10 structure. So what does it mean? The word 11, for example, in Chinese is equivalent to 10-1. So the meaning of the number words past 10 is obvious. Languages such as English or Spanish have less obvious number word system, and some of the number words in these languages do not map clearly onto a base 10 structure. So for example, instead of 10 and 1 in English, we call that 11. These different number word systems can impact how children learn to count. Research suggests that children learning languages with more transparent number systems, such as Chinese, Japanese, or Arabic, may have an easier time, at least at the beginning, in learning to recite numbers, especially numbers that follow 10. Multilingual learners may learn and communicate mathematical ideas in more than one language. Children should have many opportunities to use math and express their mathematical thinking in their home language and in English. Our next focus is on inclusive practices to promote mathematical thinking and engagement. It is important to consider that children may communicate their understanding in various ways through spoken language, nonverbal gestures, sign language, and other forms of communication, such as a picture exchange communication system or an electronic assistive technology communication device. It's possible for all children to demonstrate their mathematical knowledge when provided the appropriate supports and adaptations. And these include environmental adaptations, such as changing seating or minimizing distractions for children, material adaptations, for example, technologies or adaptive equipment, and instructional adaptations, different communication modalities, and modeling and different teaching practices that support individual children. Our next section focuses on how educators can support children's math development. The foundations have many supporting sections and examples for how teachers can support children's math development. We will highlight here a few of the main categories of teacher strategies and instructional support. The first one focuses on scope and sequence and planning instructional activities. Early childhood educators play a pivotal role in helping young children develop their understanding of mathematical concepts and skills. Preschool-age children benefit from regular, systematic, planned mathematics activities with specific learning goals, which can be part of an evidence-based curriculum with a scope and sequence. Children need to work up to more complex math skills and concepts, and therefore should be provided with more advanced learning opportunities over time, ones that build on their prior skills to develop more complex mathematical thinking. Educators scaffold children to support them in individualized ways in their math development. Next, we focus on practicing mathematical concepts in everyday routines and play. Children can learn about mathematical concepts through daily routines like mealtime, shopping, setting the table, through interactions with peers and adults, and through play. Play provides children with meaningful and joyful opportunities to engage in mathematical thinking and problem solving. For example, deciding how to evenly share 4 shells between 2 peers. As children play, they can develop deeper conceptual understanding of mathematical ideas by making connections between seemingly abstract concepts and real-world experiences. So, for example, through play, children begin to understand that sharing is a real-world example of division. Teachers can facilitate this learning by inviting children to solve problems they encounter in their play and asking open-ended questions to expand and deepen children's learning. For example, how do you know that you both have the same number of shells? Next, let's focus on math materials. Learning environment with varied open-ended materials allow children to explore mathematical ideas and develop important mathematical skills in the context of teacher-planned mathematics activities and as part of evidence-based math curriculum, and of course, everyday interactions and play. So materials play a role in all of these contexts. Open-ended materials that vary in attributes, such as size, shape, or color, allow children to practice various mathematical skills, such as sorting, creating patterns, measuring, and composing shapes. The open-ended nature of these materials also support children of diverse backgrounds skill levels, and interest to take part in mathematical learning. Now, when available technology can be used to represent mathematical problems and ideas in new ways, such as asking children to solve puzzles or play shape matching games on a computer, that's an option too. So providing children with a variety of objects and materials that promote mathematical exploration is really essential for their mathematical learning. And last but not least, incorporating home connections. Incorporating home connections is a powerful tool. We touched on this earlier. One way educators can nurture children's interest is by integrating children's home language, cultures, and racial and ethnic backgrounds into mathematical learning experiences. For example, educators may decide to introduce ways of children to engage in mathematical skills when preparing cultural foods. So, measuring out the ingredients when preparing a dish. Given the important role that families play in children's mathematical learning, teachers can learn from families how mathematics is already part of their family's daily activities with their young children, and to build on those experiences in the early childhood classroom. Teachers also can engage families and communities in children's mathematical learning and offer ideas about how to incorporate mathematics into their daily lives and home routines. So, for example, counting while grocery shopping, measuring while cooking, or sorting while doing laundry.
So that concludes our webinar. And for a more detailed view of the mathematics domain, please read the full document published on CDE's website. And there will be future pre-recorded presentations. Also will be posted on the CDE's website as they are released. And to visit the website, you can visit https://www.cde.gov/re/p/foundations.asp. Thank you for listening to today's pre-recorded presentation.